All right, we mic'd up? Cool. Hey everyone, thanks for coming. The talk that I'm giving called Rethinking How We're Linking. We can start a little introduction about myself. My name's Loren. I'm a software engineering manager at Meta. I work on the Python Language Foundation. I was previously an IC on the same team. So I'm talking a little bit about what I did over the past couple of years as a IC. You can see in those pictures, I have a dog who I love, play some music, and do some other hobbies because I'm a real person. All right, so what I'm talking about, very, very, very high level, talking about statically linking C extensions into Python applications and how it can improve performance. So that's hopefully something you'll understand a lot better, what I mean by that by the end of the talk. Some effects of that, all right, so who doesn't love big numbers? One example of a place where we implemented this and used it was for Instagram, where we saw a savings of about 2 megawatts, which is the average energy usage of maybe 1,600 homes. And that's one application. This has been rolled out to about 90,000 or more applications. And beyond those efficiency wins, we also saw a lot of build speed wins. And building Python's a thing you do when you have a ton of native code. And this is in comparison to a thing we had before, but seeing more than 5,000 hours a week of time saved. So quick agenda of how we're talking through this. I'm going to go into an example of how to build a Python C extension, comparing that with the same tool built in Python and built in C. Talk about when things slow down, what happens when you have more imports added. Going to dive into a little bit about static versus dynamic linking. I have a fun little analogy we can go into there. Talk about what I came to talk about here, native linking C extensions, what that looks like, what embedded extensions look like, and then go into looking a little bit about why things were slow. So first off, this Python C extension example. So a fun little example here, talking about, say you have a company and you sell bananas. Every time you get an order, you log the zip code. And we want to be able to take in a list of zip codes and see how many bananas were purchased in that area. What we're looking at is we need kind of 3 functions for this. A main, which is going to kind of parse the input arguments. This will have the data file that has that list of zip codes in it. And then it'll take after that just the list of zip codes we're searching for. We're going to implement this with a load file that is going to open that file that's passed in, load all of the data into it in a global array so we can search it. And finally, count orders, which is what's actually going to, you can pass in your zip code to that, and it'll count the instances of that in this global data array. So first thing we'll look at is the Python implementation. I've here just quick setup at the top of the file, and you can see we're just importing sys and argparse, and we're defining this global data array. We have our count orders function, which uses the Python list built-in count to look for how many occurrences of that zip code there is. We have load file, which then takes in a file name, opens that file, reads the contents to our data array. And we have our main function here, which is using argparse, which we imported above, defining a couple arguments we're passing in. So the data file, the list of zip codes, that nargs there equals star means you can pass in any number of arguments, and it will include them all in a list for you. And then we iterate through those passed in, and we print out the count for them. So we can go take a look at what that looks like here. So let's open up this. And is that font size okay for everybody? Cool. You can open up this file. You can see it's exactly as I showed you. I'm not lying about it. I don't think I changed anything since I put the slideshow together. Does all of those things. So I have here this orders.dat. And you can see there is a large number of lines in that file. It's a lot of zeros, so it's hard to tell without commas, but it's 10 million, because I generated that file myself. So that's kind of a big file to read in. So let's run this. We can do Python 3 count orders.py. We pass in the name of our file, and then we give it a zip code. 97451 is zip code where I grew up. You can see there's 105 orders from there, so pretty bananas. That happened not too slow, right? Let's go ahead and we can run this with the time utility. You can see it took about 1.2 seconds. So not crazy fast, but not crazy slow. Things get a little slower when we want to process more. So instead of just looking up one zip code, let's look up maybe 50 zip codes. So here we can use head to print out the top 50 lines of our orders.dat, when we can pass it as arguments to that function. We can go over here, get rid of that one, and we can run that. Now things are a little slower. It goes, still going in about 4 seconds. So not near as fast as we would want with that. So we can go back and take a look at a C implementation. So say we had the same thing implemented in C. We have a header defining here, and it's defining our count orders, it's defining our load file. Kind of count orders is, again, just taking in that zip code as an integer, and then load file is taking in the name. We have our zip code data.c, so this is pretty much the same as the imports that we had at the top of the Python file, except for here we're saying bring in our header that we wrote. We're defining here that list of data, and we have to give it a set length because we're in C and it's not dynamically reallocated, but passing in that. So one big limitation here is we have to define that all up front. We have our count orders function here. So again, it takes in that int, it iterates through that entire array of data that we have, and every time it sees a matching zip code, it'll increment our count and return that. And we have our load file, and this does pretty much the same thing as our Python implementation, or almost exactly, right? It opens this file in read mode, and it scans through it, pulling out an integer from every single line and putting it into our data array. And then we have this count orders.c, and this is the same as kind of our main function that we had in the Python file. It takes in the 2 arguments, it calls load file, loads count orders for every single one of them. There's a couple more things going on here, of like when it has to convert the arguments to integers and kind of where it's printing them out. So because we're using native code here, this is something that we have to build. We can't just go and run it. So we have a build defined in this make file, and we have, let's see, 3 build targets. Make files, if you aren't familiar with them, you define a build target, which is the thing in the teal on the left. After that, you define the dependencies that go into it. So those are the files on disk that it'll check. If that file is changed, when you run make for that target, it'll rerun it. And then underneath, you have the commands that are ran to be able to build that file. So here we're using Clang, which is the compiler here. And you can see, so the first thing we're building is we're compiling our zip code data.c. That's our C library for it. We're compiling our count orders.c, which was the main function. And then we're linking the count orders into an executable that we can run. So you'll take a look at what that looks like. So let's, man, I keep typing C instead of E. Let's open up our count orders.c now. And you can see things are about what I said they are. We can take a look at our zip code data.h. And you can see same as that. And let's look at our make file. And again, there's some more stuff hidden down there. We'll come into that later. But right now, we have these 3 things. And what we're going to want to build here is this count orders. So let's go ahead and we can do make count orders. Runs for a second. All right, now we have this file here. We can take a look at what that is. And we can see it's a 64-bit executable. And we can run it. So /count orders. Let's pass in this orders.dat and let's do that same 97451. Takes a minute in the first run as things get loaded. Okay. So let's see how long that actually took. It runs about 0.6 seconds, so twice as fast as our Python implementation. And where this really shows improvement is when running multiple. So let's take a look at the top 50 of these again. And xargs there. And it runs the whole thing in pretty much the same amount of time. So this is where we're seeing the significant improvements, right? This is 0.6 seconds to go through and look up all of these as opposed to the 4 seconds we're seeing in Python. So how can we improve our Python implementation to see similar speeds? Luckily, Python has a way of building C and C++ extensions. So this is integrating in the code that we wrote with C into a Python module. The main things to look out here is that it is a shared library on disk. So it's a .so file. And then there's the pyinit function, which is what initializes this module as a Python module. The pyinit underscore module name needs to match what we're importing. So I have defined here a zipcodes.c, and this is that C extension. You can see we have two functions defined, this load file, count orders. Currently they're just returning none, so we're gonna implement those in a little bit. We can see the method definitions, and this is defining these methods for building out this Python module. And then both of them are there. And then here you can see our module definition, which is telling it to include that list of methods that we have. And then we have our PyModule init function, which is what Python will then use to create that module. And again, since we're using native code, this is something we need to build. With Python, we need to include the python.h header that is at the top of those. So that's that python3 config -- includes. We'll give you the directory to that for your installed Python version. And then for the .so module, we need to include the proper LD flags, which is telling it what shared libraries to link against. So let's take a look at what that actually looks like. So here we could do our make zipcodes.so. Takes a minute, it builds it. And let's take a look. We have our file, zipcodes.so. Okay, so this is a dynamically linked shared library. We can run just a Python interpreter here. We can import zipcodes.so, or not .so, just zipcodes here, and we get our module. We can see right there, is this module zipcodes is defined from that zipcodes.so that we had. We can do zipcodes.load file, returns none, just as expected. So let's go and actually implement this and make use of some of these things we have. So actually, I'm gonna open a whole new session. Zipcodes.c. Okay, so we have this, which is our Python file, and we have our library functions already defined in our header file, right? So we can open up our zipcode data.h, and we can see we have our count orders and load file. So we can just reuse these functions over here. So we have this one, which is our pyload file. Let's go here and do a new line where we have that none, and let's change this up. So pyload file, we want to take in a string, and we want to call that load file function. Python provides some C API methods for things like that. I'm not going to do any data validation on my arguments or checking of things, which is a thing you should probably do if you're doing this in real life, but because I'm coding it live, I think for the sake of brevity and simplicity, we're just going to make use of things as they are. So we can make a const char star, which is how you define an array of characters for a C string. And we're going to call this file name. And we can make use of the PyUnicode from UTF-8. And we just pass in our argument to that. So what this PyUnicode from UTF-8 is, it's a C API function that will take a Python string object, which is PyUnicode under the hood there, and it will convert it into a C string for us to use. And then we'll call load file with our file name. And to make sure this works, we want to make sure to include our zipcode data.h. So with that included in there, and that added, we'll be able to load the file into memory. And to do the thing we really want to do and count the orders in it. Okay. Here, we're getting in this argument again, and here we're expecting an integer argument. So we can define our int zipcode, and let's do pylong, because that's how we can pull these things, pylong as long, and passing in our argument there, which will convert that Python integer into the C integer. I mean, just creating it as a long, we're casting it into an integer. Don't worry about data overflows, because again, we're not doing validation here. Okay, so we have that, and we can call our, let's get our int count equals count orders zip code. And then we want to return a pylong from long. So just kind of doing the opposite of the change that we did there. Cool. So that just kind of changing the arguments from Python into types that we can use in C, calling into the functions we've already defined, allows us to define a Python module that will use what we have in the C. So let's open up our make file, because we need to move some things around that. Okay, so here we're looking at where we're making this zipcodes.o, and we're compiling zipcodes.c. We need to make sure to tell it to look at our header. So we'll do a dash include and zipcode data.h. So now when it's compiling, it'll also take a look at that C header, which is defining those functions we're using. When we're making the zipcodes.so, we want to make sure to include with it into here our compiled C, so zipcode data.o, and then our link line here. So what this is doing is we're telling it to compile it or link it together. I'll put it into the zipcodes.so, is the file it's creating. It's a shared object, so this is that dash shared. And then the code we want it to include is in these object files. All right, so zipcodes.o has all of our Python module definitions, the pyinit function, everything there. And then the zipcode data.o is going to have our the zipcode data functions we need. Line 16, I missed dash I. Oh, thank you. Cool, that'll keep things from crashing when we go and run this right now. Or maybe it won't, actually. So let's clean what we've already done, and let's do this make zipcodes.so. And hopefully, and I made an error somewhere. All right, incompatible integer to pointer conversion, additionally constant star with an expression of type int. It's as, yeah, I made that mistake in one of my practice runs too. PyUnicode, not from UTF-8, because we have a UTF-8 already. It's as UTF-8, because we're taking our Unicode object and turning it into that. All right, let's pretend that didn't happen and try again. And there we go. It looks like it works. So we can open our interpreter again. We can import zip codes. We now have our module. We can do like zipcodes.load file. We want to give it our file name of orders.dat. Run that. Takes a second because it's actually reading that file and everything to memory. And we can do a zipcodes.count orders and give it that 97451. It runs 105. Cool. So let's actually make use of that. Let's open up our, what did I call it? Count orders.py. Open up this file, and we don't need any of this anymore. We're going to use our C module. We can go down here and do from zip codes import. What do we have here? We have load file, and we have count orders. Okay. And now I think we should be able to just run that, right? So Python 3 count orders.py, orders.dat, 451. Run it, 105. And we can look at the timing of that. And it's about 0.6 seconds, so pretty close to the speed of our C implementation. And again, the more exciting part is what happens when we pass in more arguments and are searching through that list multiple times. We get in about 0.7 seconds. So it's just as fast as when we wrote this completely in C, except for our interface into it is now our Python file. We can use things like argparse to actually check the attributes being passed in, what we expect them to. We can define better help information and all that benefits we get from writing in Python. And under the hood, we can do it just as fast as we were doing it with C. Okay. So that seems well and good, right? We wrote a C extension. It's significantly faster than what we wrote with Python. But we're talking about what happens when it's not quite as fast. So you'd expect it to be much faster. But the problem is, in some much larger binary cases, again, Instagram is a fun example of this, there's thousands of C extensions that can get imported. And beyond that, there's tens of thousands of native library dependencies. So these are other shared objects that when you import a C extension, it then goes and loads all of these ones into memory. And that can start to significantly slow things down. I did a little benchmarking. I created a very simple tool that auto-generated X number of modules, and then a script that would go through and import every single one of them. So this is using just pure Python. Right? So this is a bunch of .py files on disk. For each of them, the PYC is pre-compiled for them too, so it doesn't have to compile PYCs, it's just loading them in and loading the modules. And we have pretty decent import times, less than a second, even up to 8,000 modules. When we do the same thing with CExtensions though, see it gets significantly slower, much faster, right? This is not linear. I didn't do the math to see what direction it is, but it definitely, things slow down quickly. And we're looking at about 3-second imports for these 8,000. And again, these are very, very simple modules that we're adding here. I think each of these CExtensions just has like a single method on it that returns a string. And each of the Python modules just has like a name defined in it. So went to go take a look at what was taking so long in these imports. So taking a look at it, we can see, and this is output from Callgrind, which is a tool that you can use with Valgrind to just count the number of calls to specific functions. It's slow if you have something really big, but for something small like this, it's pretty easy to get this output from it. And we can see there's this function dlopen. Oh, I can't use my mouse to point to things, huh? Right here. And this is taking about 92% of the time. So dlopen is the function that is what loads a shared object, and it's what Python uses when it imports a CExtension. To dive a little deeper into it, I kind of open this in LLDB, put a breakpoint at dlopen to see where we're being called from. And you can see it's in this underscore imp create dynamic, which then loads the dynamic module. So this is during the import of CExtensions, tracing back where imp create dynamic is called from. This is just a link from underscore bootstrap external.py, which is in the CPython source code. At the end, I have all of these links written out, so you can copy them from there. And you can see in this create module function, it is where we're here calling imp create dynamic. So it's the CExtension imports that is leading to the dlopen calls, which is what is causing the slowness on this import time. And yeah, loading shared objects is expensive, especially when you get to very large numbers of them. Okay, so we're here because I was going to talk about static linking versus dynamic linking, and how we went to statically link CExtensions. First, I think it'd be good to do kind of a quick overview of the differences between them two. I have a fun little analogy that I put together that I think kind of helps explain what's going on there. So say you have a grilled cheese restaurant, right? When you first start cooking things, it's simple. It's just you working there. You have your recipe, your ingredients, your griddle, everything right in front of you, easy to go. This is very analogous to statically linking a small program, right? You have your recipe, which is all of the code, your ingredients, which is all of the data, your griddle, so everything you're working with. But things start to grow, right? Cheese Louise is doing well. It's time to expand. You get more people in the kitchen. And now you're just duplicating this exact same setup for everyone there. It's a small kitchen. Things are getting tight. So you try and figure out a way to save space and realize that you can put all the ingredients in a fridge that's everyone shared by everybody. You can put all the recipes in one recipe book everyone can go to. And then when someone's cooking, they grab what they need for the specific thing, they take it back, they work on it. So this is analogous to dynamic linking, right, where you link everything into this shared object that is then shared between every one of the programs. But when you get significantly more shared objects, things get a lot more complicated. And this is where you're going to look something up. You have to find exactly where it is in the fridge, looking at every single name along the way, and that's where all those string compares are happening. It gets significantly more expensive to go look things up as you have a lot more shared objects. And then bringing it back to static linking, right? We can take it when we have a ton of things, and we can all link it into different, statically link it into its own binary. And in that case, you have your station, you have the ingredients for exactly the things you're making there right in front of you, if the recipe is right where you know it, and you can be quickly working through things again. Okay, so I think it's probably easier to explain this by taking a look at what I'm actually talking about here. If we open up our makefile, we have here, we can just look at our initial count orders, our C program. Right now, we can see our count orders is linking in just both these .o files. So what we're getting here is a statically linked program. So we can look at this. We can take a look at the things that are inside of that, right? So nm is a tool for printing out the internals of a binary, and we can look at using it for looking at the symbols that are defined in this count orders. So we can do count orders, and name count orders no such file or directory, because I did a make clean earlier, and we need to actually build it. Now it builds. Now there is a file or directory, and we can see it's pretty simple. It has count orders, that function that's in it. It has the data. It has links to fopen and fscanf, which are those functions that we're using for opening and scanning through our file. And it has the load file, which is that other thing that we have defined in our zip code data, and links to a couple other functions that we're using there. And we can take a look at like our zip code data.so or .o. I actually have to spell things right, huh? And again, right, this has the count orders defined, it has the load file, and it has the pointer. So all of this is exactly what is in our count orders executable, because when we're statically linking, we kind of take all of this and copy it directly into there. So we can actually change how this is doing it. Take a look at our make file. What if, with our zip code data, instead of just creating a zip code data.o, we turn this into a shared object? So we can go down here and do a zip code data.so. This is going to take as its input zip code data.o. All of that looks like what I'm expecting. We can do a clang-o. We want to do, we're calling this zip code data.so. Yep. It's a shared library. And we want to link our zip code data.o into it. There's nothing else we're including with it, nothing else we have to link against. So we can do this make zip code data.so and take a look at what we got there, zip code data.so. Run that and we can see it has just our count orders, just data, load file, and then these references to the system functions we need of fopen and fscanf. We can now, this is a different. We can now go and update our count orders to use that shared object instead. Before we can take a look at first how you can print out some information about binaries to see what shared objects they're using. I typically work on Linux, so I actually had to quickly research what this was today because I realized LDD doesn't work because this is a Mac. But you can have dynamic loader info. We'll print out info about it, and we can run this with our count orders. And we can see right here, it's only relying on the system dynamic library, which I think is what does all the dynamic loading and stuff. Don't quote me on that. I don't know Mac very well. But what we can see is how that changes when we build count orders. Now we're here going to pass in zip code data.so instead of .o. Change it right here as well. Double checking myself so I don't forget a dash again. We can do clean so that it'll rebuild. We can make our count orders again. Okay, and now if we look at the dynamic DLD info count orders, we can see there's two dependencies. And the first one there is our new zip code data.so that we made. So that is how we can take what we had statically linked to making it dynamically linked. We could use the same zip code data.so if we want in our zip codes.so, right? We'd have to just do those same changes here. Change that to a shared object. Change this one to require our shared object. We can make that one. We can look at our dynamic loader info of zip codes.so. And yeah, look at that. We are, where are we in this one? Yeah, we can see that it's relying on our zip code data.so. And when running both of these, they're going to pull in that same file for them. Okay, so that's going a little bit into static and dynamic linking. The next thing, and what I came to talk about, was embedding CExtensions and what that can actually look like. So this is how we're going to take our CExtension, that is this shared object that we import by DL opening it from disk, to something that is embedded within our application, and we can import without having to open any shared objects. So the first thing, or what we're looking at here, is a simple embedded Python application. This has a couple of things going on in it. First thing, we're defining just a configuration. This is kind of like the most bare bones version of this you can make. And again, there's no error checking or type handling or anything like that. But we initialize our configuration. We set our arguments on it. So this is the argc and argv, taking everything that's passed into this C executable and passing it directly into Python instead. PyInitialize is what starts up the interpreter, initializes the runtime and everything you need from there. And then PyRunMain tells it to just run as if you're running the interpreter itself. So again, a thing we need to build. So we have our makefile definition here, and we're compiling our pymain.c, and then we are linking the pymain.o that we get from that into an executable. Okay, so let's do the fun part of actually making it. We can make our pymain as we expected. We can take a look at what the file is. You see it's a 64-bit executable, and we can run it. And we run it, and it just opens up a Python interpreter, same as if we had ran Python 3 there. We can take a look at maybe sys and look at sys.executable, and we can see that instead of pointing to my homebrew installed Python 3, it's now pointing to the pymain that we just built there. Okay, but we wanted to do more than that, right? We want to actually include in this C extension that we wrote. So if we go back and open up pymain.c again, there's a couple of things we can do here. There is a C API function, append init tab, and that allows you to define a C extension that will treat like a built-in. So this is how built-ins are defined, and it uses import paths kind of the same as how it works for a built-in. Built-ins are like the things that you can just import, right? Like sys, os, any of that. So we can do a pyimport append init tab. This takes in two arguments. One is the name of the module that you want to be able to look up in it. So we can do this underscore zip codes. I'm adding an underscore so that we know we're importing the embedded one and not importing that SO on disk in case I forget to delete it. And then we need to pass in the init function. So when it goes to import an embedded extension like this, it'll look through the init tab, it'll match the name of the module, and then it'll look at the init function that's included with it. And instead of opening it from disk and finding it, it then can just pull it from this list, call that init function, and initialize your module. So here, pyinit underscore zip codes is what we'd called it. And again, we're going to need a reference to this for it to actually work. I don't want to type that there. So let's see, we're going to say we have an externally defined init function, and it's a py mod init func, and this is going to be our pyinit underscore zip codes. Cool. And maybe I should spell it right. So this is saying that outside of this compilation unit, outside of this file, there's defined a pyinit zip codes, which when we build will be accessible. And then here, we're telling Python to append to the init tab, so you can call import zip codes, and it'll just run this init function. Okay, so we're going to need to update our makefile for this. So open up the makefile, because now, here in this pymain, when we're building it, it's going to expect to find that extern function. So we can include our zip codes.o. And again, we're statically linking this time as opposed to when we build it with a shared object. So we're directly taking the output from the compilation, which is that .o file. And then we also need to include all of the function definitions that zip codes needs, which is in our zip code data.o. And now we need to add this to our line here. So zip codes.o, zip code data.o. And I think that should do it for us. So let's clean and make this pymain again. Oh, I was scared that one was going to crash. And there we go. We can run pymain. We can import underscore zip codes. We have it. We can look at like underscore zip codes dot underscore loader, which is the loader that it uses to actually import it. And you can see here, we're using the built-in importer. So kind of same thing that you would use with, that other built-ins use. We can do all the same things with zip codes. We can do underscore zip codes dot load file, orders dot dat. Takes a second, it loads it. Zip codes dot, what was the other thing we're doing with this? Counting orders. Can run that. You can see there's 105 there, running all the things we'd expect. Okay, so let's update our countorders.py again. And now we would just change our import from zip codes to underscore zip codes. If we run Python 3 countorders.py and pass in our orders dot dat and give it our, change that up, it fails, right? Because zip codes isn't defined in Python 3. There's no SO on disk. Our underscore zip codes isn't. There's no .so on disk. But if we use our statically linked one we just made, and do /py main, it runs, it does the thing, because all the symbols it needs to run it are there. We can take a look at maybe our dynamic loader info of our count orders just to, what do we call this thing? PyMain, just to confirm. Right, and you can see its dependencies are just the Python libraries that it needs and the same dynamic loader stuff that we had before. Okay, so that's exciting. What does that actually get us? So if we take a look at this graph that we were showing before with the import time for Python, the import time for C extensions, now if we look at those same numbers with embedded C extensions, with even up to 8,000 of them, we're seeing significantly faster imports. There's some pieces I kind of breezed around here. One thing is we don't use append init tab when we're actually doing this for any of our builds. We have a much more complicated, we use Buck2 as our build system, allows us to do a couple more things, and there we generate a standard unordered map. So we're using just a C map so we can have much faster lookups instead of having to look through the entire init tab for these functions. But there we go. We have those much faster imports. And, it was much faster than I thought. But I got to this. Are there questions regarding any of it? Hopefully that made some sense. Yeah. Yeah, so it'll improve import speed on things. There's actually, so a complicated answer to that. Yes and no. For import time, it'll make imports a lot faster. There's actually times when you're running a smaller application where we get slower startup time because now you have to load this much larger binary when you start up. One of the other big performance costs we see at import time is due to data relocations. And that is, if you go back to our analogy and look at like where they have to go to the fridge and get all the ingredients, which is the data they're using, they have to pull just their own set to their station, right? Because you can't share the data between applications. So this also significantly speeds up that part of it, which gives a lot of runtime performance wins there when things are actually accessed. But so, yeah, I don't remember the original question, but the answer is yes and no. Yeah. No, I've not looked into that. Yeah.
Is there any difference in like the size on disk of the different compilation methods?
Yeah. So actually one of the things we saw with this is significantly smaller binaries at the output of it. So some more context around that, we have a mono repo for everything. So every build is hermetic. So it includes all of the dependencies required for it at the exact moment it was built. So no two built binaries actually share the shared objects between the two. So we don't get the memory savings or savings you get regularly from using shared objects. But when building everything statically linking, it allows the linker to do some optimizations on it. So this means when you're linking something together, it looks at just the symbols you need and only links those into the binary, and it's allowed to throw away the rest of it. Again, if we want to compare that to our analogy, right, you're building something, you only need to look at the ingredients on that recipe of what you have and pull those over, and it reduces the amount of space you need.
Can you go back to the chart for a second?
This one?
Yeah. Does that feel to you like
Yeah.
Run it across like older kernel versions.
I didn't do a lot of testing across things. I was building my presentation and actually got into the rabbit hole of trying to figure out why, because I saw like significant number of string compares. I'm wondering why there's like worse than O of n string compare on DL open and what's happening there. But before I got too deep, I pulled myself in and had to write the rest of this. Yeah.
Follow up to that, this is a well-documented issue for sufficiently large projects such as OpenOffice.
Okay.
Most people don't hit it, but really large ones do.
We'll run into this.
It'd also be interesting to see length of symbol names, stuff.
Yeah, how that affects it. Yeah.
Yeah, so is this, I guess the reason that you want to cut this import time is because you're deploying this in like an ephemeral context, is that right, generally?
Yeah, and for CLI tools, we want faster runtime, and for startup of applications that like take a while to start up. Yeah.
So I can define essentially for every different application, you're essentially building a different entry point, you call it a module for that application.
Yeah.
Does that become harder to maintain, or like keeping the modules that embed that and recompiling? What's the developer experience around that?
Yeah. So in our previous way of building, we'd need to recompile for every single building binary you're making anyway. And in that case, we'd recompile all of the shared objects and their dependencies. In this case, we're moving to just this single step that's recompiling everything into this one large binary. There is some kind of housekeeping along the way, right, of creating that map that I was talking about, which is how we can look up these PyInit functions. We do that through a bunch of, we have Python scripts for generating C files that we then link against when building. Yeah. Yeah, so that's going back to like talking about relocations and the relocation cost. So for significantly larger modules that have a large amount of data that needs to be relocated, we no longer have to pay that cost at import. So it significantly improves performance, kind of even more than just in the case of the small, simple modules. Cool. Well, I guess I have my links. I can share those. I also didn't expect to get this far because I was a little slower in my practice. But there's other fun things we can talk about. So I kind of did prepare for something to do here if I made it. One of the things that you could run into, and this is one of the things we ran into, is symbol collisions. So if we go back and we look at our example, we have our zip codes, right? So let's open up this zip codes.c. What if we had another function that was very similar to zip codes.c? All right, so we can just go ahead and copy zip codes.c and call it like a zip codes.c. Okay, and let's open up our new a zip codes.c. And of course, our init function name has to match. So we can have that a zip codes, and we need to be able to build it. So we can just go ahead and copy these two lines, do this here, and let's do this. What are my lines? Okay. We have line 24 to line 28. Let's do some replacing. Let's replace zip codes with a zip codes. Okay. That was a find and replace thing we did there, and now we have this a zip codes.o and this a zip codes.so. Uh-oh. I just typed something wrong. We can make our a zip codes.so builds as expected. We can make our zip codes.o or .so as expected. We can open up Python 3. We can import zip codes. We can import a zip codes. Both of them work, no problem at all. But what if we want to statically link both of these now? So we can open up our pymain.c. We now have another module init function that we're including. This one is a zip codes. We now need to do the same thing with our init tab. Underscore a zip codes, pyinit. Okay, and let's update our makefile again. So now we have our pymain also requires a zip codes.o, and it requires an a zip codes.o in this line. Okay, so let's move pi main again. It runs, and it doesn't work very well. So this is because in both our a zip codes and our zip codes, there is multiple definitions of these pi_pi count orders. That's the thing the linker doesn't like, right? We're putting everything in the same place. There's two things with the same name. Doesn't know which one to use or how to resolve that. So there's a couple of things we can do about this. The route we went with it, I guess the correct route, or probably the cleanest, nicest thing to do is to go and edit things and make sure no two modules share function names. When you're looking at the scale of some, tens of thousands of these, that's not something that is actually does not make sense or is not easy to do as well. So there's other tools for that. One is LOVM. I had to change all my tools. Copy, which says no manual lynching. This was the unrehearsed part. And here, there's a bunch of things that it does. Does it give a nice top heading of what it does? Nope. Pretty much, this is a tool that lets you modify a built object. Right? So what we can use it here, and what we use it for, is renaming symbols in some of these output files. So there's another tool, like I was showing before, nm, that lets you print what's in it. So we can do nm a zip codes.o, look at everything defined in there. We actually only care about the external and the defined symbols that are in it. So external are symbols that can be seen from outside that file, outside the compilation unit, and defined are things that it's not pulling in from somewhere else, but they're actually defined in there. So if we look at those ones, and we think about, and we want to rename some of them, we can do this. See, obj copy there. It's LLVM obj copy here. Obj copy, dash help. I think it's like rename symbol. I should have remembered these things. Not rename section. It's not symbol file. Redefine. Thank you. Redefine. There's a redefine sims that you can pass in a file name. This file is a list of symbols, which is on the left, it's your original symbol name. On the right, it's what you want to rename it to. So we can make use of our nm call we used here, right? So this will print out everything there. We can then make use of awk, which is a fun kind of text modifying thing here. And we can call it, let's see, we want to first print out our symbol, which is the third column. Okay, now we get the list of our symbols. We know that's going to be our first line there. We then need a space, and then we need our redefined symbol names. So let's do that, and then we can call it maybe _a. So that runs through, and that'll change all of our symbols to now have this suffix applied to them. We can here, we don't want to rename our pi init, so we can do a grep pi init. So say avoid doing that one, and we get that list. We can go ahead and pass that to a sims file, and now we have that file written out, right, with our how we want to rename things. We can do a LOVM obj copy. We will have our dash redefined symbols. I hope that was what it was called. Just sims, thank you. Equals sims file, and then we want to give it our input, right, which is this a zip codes.o, and our output, which is going to be a zip codes.o. Let's say like .renamed.o. Run that. Now we can look at our a zip codes renamed.o and see that we have our pi count orders, pi load file. All of these things are suffixed correctly. You can actually even open up our make file and tell our PyMain to use our azip codes .renamed.o, and we'd want to, add targets for each of the opt copy things that we did before, but we can now make PyMain with that instead, and it's able to link together. We can take a look at what's inside of our PyMain now, and we can see it includes both underscore PyCount orders and underscore PyCount orders, PyCount orders underscore A. So yay, we got past that problem. Any questions? I ran out of my post-talk talk too. Thank you.
I'm curious how you knew that the imports were things as well in the first place. Like, it's really obvious when you lay it out like this, but I don't know.
Yeah, I just was kind of looking at just really slow startup times for things that shouldn't be slow to start up. Right, so you have a CLI that's just printing -- help, and if it's taking, I don't know, a minute or 2 minutes, then there's something going on before help is running. You can dig in and see if there are side effects on imports, but then seeing that it really was like the time to import all of these. Python has a useful thing that is profile import. It's some environment variable you can pass, Python profile imports or something like that. If you turn on, it will actually print the import time for every single thing that's being imported. So actually, I used that to print import time for something. I was looking at where things are really slow, and I combined that with LD debug, which is another environment variable flagging class on Linux, to tell it to print when libraries are being imported. And I could see where it would say like it would start to import something and it'd be a really slow import, and there's just this huge list of SOs that were pulled in at that time. And like comparing those and saying, okay, the slowest things are having the most shared objects, and kind of going from there. Yeah.
I don't know if this applies, but C++ don't they mangle the
Yeah, they do mangle symbol names. There's ways of getting it to work with obj copy. There's arguments you can pass it, tell it to not demangle it when it prints it, or yeah. Cool. Well, thank you. I have this here. There's resources. I don't know if you're able to actually get the slides, but you can also take a picture and have the AI of your choice parse those into actual things you can click on. All right, thank you.